Hey dudes, Dude the Builder here, and in this episode of Zig Master, we're going to be using what we've learned about allocators and pointers in Zig, and we're going to create our very own data structure. It's what's known as a stack. A stack is a data structure in which you can store items, and you can retrieve those items, removing them from the stack. And the word stack pretty much refers to how it behaves. It's a behavior that's described as last in, first out, meaning that the last item that you add to the stack is the first item that's going to come out when you retrieve an item from the stack. Basically like a stack of plates. And that process of adding an item to the stack is traditionally known as pushing to the stack, and when you retrieve an item and remove it from the stack, that's known as popping from the stack, and those are the terms that we're going to be using. The standard library already has a stack-like structure, which is basically the array list, which we've seen in previous episodes, and that's a really pro version of a stack that has pretty much all the functionality that you would ever need out of a stack data structure. In the array list, instead of pushing, you have the append family of methods, but aside from that, it's pretty much the behavior of a stack. And this stack that we're going to be creating, it's going to be a really simplified version of a stack compared to what the array list can do. Okay, so we have this empty file here that's called stack.zig. And the first thing that we're going to be adding here, let's add here the import of the standard library. And we're going to be needing here, let's say, mem, stud, mem. And let's start out here our data structure with pub const stack is a struct. Okay. And in this data structure, we are going to have just a few fields. We're going to be storing our allocator that's passed in when a user of our stack creates the stack. They have to set the allocator that we're going to be using. And we're going to be storing the allocator because there are the operations of adding to the stack will require allocation. There's another way, another approach that you can take, which is not storing a reference to the allocator in the data structure, and then in each of the methods that require allocation, you take the allocator in the methods as a parameter. But in this case, to keep it simple, we're going to be adding here the allocator, and this is going to be a mem.allocator. Okay, and we're going to need an items, and this is going to be a slice. Let's say that the type of this stack is going to be bytes, slice of U8, and we're going to need a capacity, and let's say this is a U size. Okay, so basically what we're saying here is that our method of storage is going to be this items slice here, and we need it to be mutable because we need to add and remove to this slice, and the capacity is going to be how much memory is actually allocated, and this is different from the actual slice of items, and you'll see why this is a useful strategy to have in this type of data structure. Also, let's give these fields default values. Here, this is a literal that basically will coerce to an empty slice. We're taking the address of this empty tuple literal here syntax, which will basically, the compiler will see that what we want is a slice of U8, and since this is empty, it'll coerce to an empty slice. And the U size, the capacity here, let's set it to 0. And the allocator, we can't set that to a default value. So the user, when they create an instance, they have to set the allocator. Okay. Another common idiom when we're creating a struct in Zig is to use a reference to the struct itself. Let's say here const self equals, and we use the this built in. So this allows us in our methods to use self as the type of the struct itself. And since the user only has to set one field, which would be the allocator, we're not going to be defining an init method, but we will need to define a sort of d'init method to free the memory once we're done with our stack. And since we don't have an init method, and actually the plan would be to free the memory and basically reset the stack so you can use it all over, start over. I'm going to be calling this method free and reset. Okay, and for this we need self to be a pointer to self, because we need mutable access, and this will not return anything. And the first thing that we want to do is we want to check our capacity, because the capacity is a reflection of how much memory is actually allocated. So if self.cap is 0, we want to return. Okay. We basically don't want to do anything else. We don't have to do anything else. Otherwise, we want to free the allocated memory. So we're going to do a self.allocator.free. And to free, we need a slice. Okay. And the way that we're going to be working with our memory, as I mentioned, the items slice is going to be a slice of the memory that's allocated, and the amount of memory that's actually allocated is reflected in the capacity. So you can have the item slice. It could be actually, let's say, 3 items, and the capacity may be 8. Okay, so the actual memory that's allocated is reflected by the capacity and not by the length of the item slice. But if you remember when we talked about slices, a slice is a structure that basically consists of 2 fields. It has a pointer, which is a many item pointer to the data type of the items of the slice, in this case U8. And it has a len field, the length, which will tell us how many items there actually are. So that many item pointer is the way that we can access the whole memory that we have allocated in combination with the capacity field. And what we can do is we take advantage of the fact that, let's do self.items.ptr. As you can see, the type of this is the many item pointer to a U8. And with many item pointers, we can use the array indexing syntax and also the slicing syntax. So we're going to create a slice here using the slicing syntax. We want to go from 0 to self.cap. Okay. This would be a slice of the entire memory that is currently allocated, and that's what we need here to free. So we do that, and then we want to reset our data structure. So to do that, what we're going to be doing is self.items equals, once again, the empty slice, and self.cap equals 0. Okay. Now what we're going to be doing is we're going to be handling adding items to the stack. And with that, let's create a method called push. We're going to be needing, once again, a pointer to self, because we're going to be mutating the data structure. And we're going to need the item that we want to add. Let's say here it's a U8. And this can fail because it's possible that we may need to allocate more memory. We're going to be seeing that in a moment, and we're going to be returning void. Okay. Now the first thing that we want to check is if we actually need to allocate more memory. So let's do an if here. If self items.len plus 1, because we're adding one item, is going to be greater than or equal to self.cap. That means that in order to be able to add this item, we're going to have to allocate more space because we've reached the capacity here. So what we're going to be doing, we're going to be calling a function that we're going to be defining in a moment, and that function is going to allocate, so we have to use try here. It can fail. Self.grow. Okay? And once we do that, we can be pretty sure that we have the necessary space. So what we're going to be doing is, once again, we're taking advantage of the fact that we have a many item pointer within the slice. So self.items.ptr and self.items.len, okay, equals item, and then self.items.len plus equals 1. So what are we doing here? Well, normally you can't store, you can't access the index at the len of a slice, but since we're dealing here with a many item pointer and we're basically using the indexing syntax, we know that we already have enough memory allocated because we just either we already have enough space and this if is false, or we didn't have enough space and we just allocated calling grow and it was successful. So then we can here, we know that we have more space than self.items slice is actually reflecting. So let's say, for example, we just grew the capacity to 8 and self.items was at 3. That means that the length was 3, and since Zig is a zero-based indexing language, when you have the length of 3, the last item index is going to be 2. So knowing that we have now additional memory past that length of 3, it means that since we're going to be adding one more item, we can use that length as the index of the next item. Okay, so PTR, this would be in this hypothetical example, this would be PTR 3, okay, which is one past the previous the length, and then we set that to the item that we're being passed in, and then we actually increment the length of that slice. Okay, so here in that hypothetical, one more time, the length would now be 4. Okay, the length would be 4, and at index 3 we have the item that we just added. Okay, now let's take a look at implementing that grow function. This function doesn't have to be part of the API, so it doesn't have to be public. And we called it grow, self, pointer to self. And once again, this can fail. And since we're going to be mutating the items slice here, we want to save the current length. So let's say here old len equals self.items.len. Okay. And we want to calculate the new capacity, new cap equals, and here we're going to need, let's move back up here, let's add here a constant called growth factor, and let's set it to 2. So basically what we're going to be doing with that is that when we need more capacity, we're going to be multiplying our current capacity by 2 and that's what we're going to be allocating. And since we start out with a capacity of 0 and we're doing multiplication, we have to make sure that we're not multiplying by 0 and just staying at 0 all the time. So here we have an if self.cap equals 0. We want the new capacity to be 8. Otherwise, we want the new capacity to be self.cap times growth factor. And now we're basically ready to actually do the new allocation, and for that we're going to be using a new method that we didn't see the other episode. We saw create and we saw alloc, but we also have at our disposal, here's self.items is going to be try self.allocator.realloc. Okay, and realloc, what we'll do is it'll allocate the space that you need, and this can either be growing or shrinking, and it will if it has to allocate a different area of memory, it will copy over the items from the existing allocation to the new allocation. So what we're going to do here is the old allocation would be self.items.ptr, once again 0 to self.capacity. Okay, and here would be the new capacity. Okay, so on success, what this is going to do is that our new self-items slice is going to be all of the newly allocated space. And now we have to basically update the state of our stack. We're going to say that self.cap equals new cap, and self.items.len equals old len. Okay, and why do we want to do this? Because the items slice isn't the same as the whole allocated memory. Okay, the amount of memory that's actually allocated is determined here by the capacity, but the actual items that are valid in that allocated memory is reflected with the item slice, and we haven't added any new items here. We're just growing the allocation, so we have to set the length of the slice of items back to the previous length that we had at the beginning. Okay, so now with that we basically have our push method. Now the next thing that we would do is our pop method, and this will be part of the API, so we make it pub pop self pointer to self. And here we're going to be returning an optional U8. And the first thing we want to check is if we have any items. So self.items.len is 0. We return null. Then we can decrement self.items.len minus equals 1. And then once again we are going to use our many item pointer to access that item, self.items.len at the length. So for example, let's say that we have that self.items.len was 4. Okay, that means that the last index was 3. So now when we decrement here the length, it's going to be 3, and then the last index that's going to be valid in the slice is going to be 2. And here we're actually going to let me add here the return that item using the many item pointer that was just passed, which is now the len of the item slice. Okay, so this is basically all we need to do in terms of pop. So in this implementation of pop, we are not shrinking the allocation. Okay, that's something that depending on the circumstances, you may want to adjust the size of the allocation. But here, to keep it simple, we're just adjusting the size of the slice and returning the item that's past the new length. Okay. Now, for convenience, when we're going to be testing this, let's add. Here I have the signature of our handy format function, so we can print out. Okay, let's use here the self. Okay. And now what we're going to do, let's do try writer dot write all stack. Just the opening here and a space. And here we're going to be using a for loop, self.items, item, and we're also going to need an index. So here let's call it I, to keep in the tradition. And if I equals 0, if I is not equal 0, which means this is not the first item, we're going to do our try writer dot write all, comma space. Okay, and then we're going to do a try writer dot print, and we print the actual item. Okay. And then finally, let me just copy this, and let's delete this, change this to the closing, add a space here. So there we go. What we're going to be doing, we add this stack prefix here with the opening curly and a space. We print out each item separated by a comma space, and then the closing curly. Okay. And with that, let's save this. Okay, we won't have any errors, so we should be good to go. Let's go back here to our main, and in order to use this, let's import it. Stack equals import stack.zig .stack. Okay, and now let's make some space here. Let's paste in our allocator. We need here a heap, stud heap. Okay, and now we're going to create, let's say here, stack equals stack dot allocator equals allocator. Okay. And then we're going to do a defer stack dot free and reset. Okay, so with that, we basically have an instance here of our stack, and what we're going to be doing is we're going to let's here in a loop for 0 to 10 I. And what we're going to be doing is, let's do a try stack dot push, and since this is a U8 and the index for a for loop is a usize, we're going to be needing here an int cast I, and then we're going to do a, let's use a debug print here of our stack. Okay, and you know what, let's make this a little more easier to read. Const print equals stud debug print. Okay, and with that, let's open up new window here, and let's do a sig build run. And here we go. We have our stack, and we are pushing the items. As we push the items, we see here how it grows. Okay. Now another thing that we can do. Let's go back to our stack. Let's add here. Let's do this with logging. In this case, const log equals .log. Okay. And let's go to our grow method here. And after, let's say after our allocation, let's do a log.debug. And let's say here, grow, let's say grew this to this, and self.cap and new cap. Okay. Let's go back here. Let's run this again. And now we can see when we are actually allocating some more space. So here right at the beginning we start out at 0, so we have to allocate, and we're going from 0 to 8. And then we are pushing here items. We don't need to allocate any more memory. But when we get here to when we need more than our 8th item, then we're going to be growing from 8 to 16. Okay, and then we finish adding the rest of the items. Okay, so as you can see, this algorithm of using the growth factor, and this is basically how the array list in the standard library works too. It makes it so you don't have to be allocating constantly each time that you push to this stack. Okay, so it's a more efficient use of the resources. Let's go back here to the code, and now let's go back to main. What we're going to be doing now, let's make another loop here for, and you know what, we can now use a while loop because there is a modality for the while loop in Zig where you can use it with optionals, something that returns an optional. And if you recall, our pop method precisely does that. Here the stack.pop will return the item, or it will return null when we have no more items. So here we have the item, and once again we're going to do here, we're going to print, let's print out the item itself, item, okay, and then let's do a print once again of the stack. Okay, so let's go back here, let's compile and run this, and now we see here we have, as we did before, we have our stack as it was growing, and the 2 times that we needed to allocate. And then here we are popping the items. We first have the item here in this line, and then we keep on popping until we get to the empty stack. Now let's do this again. Okay. And let's write this. Let's go back to that other window. Let's compile and run this. And now what we see is here we did all the popping, and now the stack is empty. And now we are pushing once again. And as you can see, we don't have any new allocations because we already have enough capacity for all of these items. Okay. Let's go back here. And what we can do is let's change this to 20. Let's go back here. And now, as you can see, we don't allocate but when we reach that we need more than 16, it's gonna reallocate and make more space, and this time it'll have a capacity of 32, and then we can finish off all the way to our 20 items. Okay, so with that, basically we have our working stack structure. One last thing that we can try is, let's go back here, and before this other loop, let's do a stack.free and reset. Okay, so we're going to basically free all the resources and set the stack back to its initial state. Let's build and run it. And now, as you can see, we do have our allocations. Once again, once we have our empty stack, we have to start allocating right from the beginning because we did a free and reset. Okay, and one last thing that we can cover, which isn't directly related to memory allocation or anything like that, but it's related to the usability of a data structure like this, is that right now it's limited to only the type of our items is U8. So we can make this a generic data structure by using Zig's comp time capabilities. What we're going to be doing here to make this generic, instead of this being directly a struct, let's instead make this, turn this into a function, a type, basically a type function. Here we're going to be receiving comp time t as a type, and this is going to be returning a type. And let's do here return struct, and down here we need an extra curly brace. And now let's search here. Here we can replace this with t. Here item is of type t. Okay, here also I'm going to be returning type t, which is the type of our items. Here in our format, we don't have to make any changes. And here in our grow method, we don't have to make any changes also. So I think with that, we basically have our generic version of the stack. Let's move over here to main, and now just have to make a little change here. Instead of treating this directly as a struct, stack is now a type function which takes a type. So let's call that, and let's say that now we are going to be dealing with F32s. Okay, and this type function returns the actual struct type. So now these curly braces and our setting the allocator here will work just as it did before. And just with that change, let's see if this will run. And we got an error here. Let's see what we have. Oh yeah, now since we're not dealing with integers, so let's go back here. Now our items are actually, let's change that. Here we're going to be needing, instead of an int cast, we're going to be needing a float from int. Okay. And we have to do basically the same thing over here. And let's see if, okay, I think that's pretty much it. Let's try this again. And there we go. Yeah. Now we're dealing with floating point numbers. As you can see here in our formatting, it's using the scientific notation here with the exponent. Okay. So with that, now we have our stacked data structure, and it's even generic. Okay, making use of the comp time features. Basically, here we can see that Zig lets us have in a function a parameter which is a type directly, and we can return a type from a function. And this, since we're dealing with types, this has to happen at compile time. So this is why this parameter has to have this comp time keyword here. And with that, we basically create our generic data structure. Okay. So that's basically what I wanted to show here. Creating this type of data structure puts to the test a lot of the knowledge that we have covered in the series up till now, using our different types of pointers, slices, and allocation, memory allocation. Okay. So with that, I hope you find this useful. Dude the Builder here. I'll see you in the next one.